Okay, so in the previous part for this lecture, we derived the basic equations for the coupled diode model, and let's now basically put those equations in the model and see if everything makes sense. So the first thing is, how did we take these equations we developed for the emitter and for the collector and put them inside this model? Well, the first thing, remember, is that if we have the emitter current and the collector current, then the difference between those would be the base current, right? So I get an equation for base current by getting the difference between the emitter and collector current. So that's how I got this equation down here, okay? And again, remember that these equations are expressed to simplify things in terms of terms like delta PE and delta PC, because that allows me to get rid of all this stuff and just write this instead, okay? Now, so how does this work? Well, let's take a look at this. If this is my emitter terminal, here's my base terminal, here's my collector terminal, what do I need to have for my emitter terminal? Well, you'll notice here for the emitter current that I have two components here, okay? I've got a component headed in this direction here, which is my normal mode emitter current component, which is here, okay? And then I could also have the emitter doing collecting, right? I said I could run the BJT in this direction where the emitter does the collecting, and that is this term here, okay? So this was the portion of the inverted mode emitter current right here that accounts for running the BJT in reverse bias. And so if I have normal mode and the inverted modes for the emitter, and they're both to this node of the circuit, then of course I've got my current here is this, because they're in the same direction, minus this, which is in the opposite direction of how I've labeled my emitter current. Okay? I do the same thing over here. Here's my collector current. I'm labeling it in this direction, and so my normal mode for the collector current here in blue is shown here. Same positive sign as collector current because they're both in the same direction. And this one is a diode in this direction here, and so this will be current flow in this direction, so it is in the opposite direction. It's got a minus symbol. That would be inverted mode for the collector. Okay? Now, going one step further, remember that in inverted mode and in collector mode, in normal mode, let's look back at the emitter. In normal mode, the emitter acts like a forward bias diode. And in inverted mode, the emitter acts like a collector, right? So in inverted mode, the emitter acts like a collector. Same thing here. On the collector, here's my normal mode. It's acting like a collector. Wow, that makes sense. Here's a collector here when the emitter acts like a collector. Here's a collector here for normal mode when the collector acts like a collector. And here is a diode here when the collector is injecting current into the base in inverted mode, where it's acting like an emitter essentially. Whoop, there's an emitter there too. So you can see both the collector and the emitter can have both emitting and collecting, emitting and collecting type behaviors, depending on which way the current's going. Last thing, again, if you look at this circuit, the base current's easy to show here, okay? The base current is the sum of all these components. So if I have current components coming in, I've got 1 times this, right? 1 times this, there it is, coming in, okay? And then I have this current going out, so this should be negative, right? And so I have the same as this, except I've got my current transfer ratio alpha out front, so this is the same as this. So the only thing I have then, instead of 1, is I have minus alpha n, because it's coming out, times the rest of this stuff here. And then I'll look at this. Well, this is going out, right? And so this gets minus, and it's alpha, right? Times this stuff. There it is. And then I have stuff coming in, so it's going to be positive because it's in the same direction as I've labeled IB here. So I've got 1 times this stuff. There it is there. And so I get the base current doing the exact same thing. So let's start to look at these things and see if they start to make sense. Let's focus on the emitter in normal forward active mode, normal mode for the emitter. Well, we already know that the emitter basically acts like a forward bias diode. It basically injects carriers into the base as you forward bias the emitter base. So if I look in this thing here, If I substitute in here delta PE into here, then this piece of N and this piece of N cancels out, and all I have left is I naught, reverse saturation current, times this. Hey, wait a second, I naught times this, that's just the diode equation. Makes complete sense. This is the diode in a circuit, right? So let's try to understand for normal mode, which is up top here, what the collector is doing then. So look at the collector here. Now it's a current source. So let me circle this a little bit to help us out here. So I'm just going to focus on, let me do this. Let's just focus on the components which are for normal mode, which is these components up at top. So here's my normal mode emitter doing its injecting of electrons like a diode. And what's going on here with the collector? Well, the equation should make sense. First, just look at the equation. The equation is basically what current is emitted. These terms are the same. So what current gets into the base, right, and is emitted, times current transfer ratio, because current transfer ratio tells us how much emitter current makes it across the base to become collector current. So this equation should make complete sense. Okay? So the last thing we need to understand then is, why do I have this current source? Why did I put a current source here? Well, think, and this is an important question, think of the basic definition of a current source. When you put a current source in a circuit, it provides current at a level that is independent of the voltage at that node of the circuit. Does that apply here? It does, because the current coming through here is not dependent on voltage on the base collector. The current coming through here is dependent on the voltage on the emitter base. Because look, in here, I've got delta PE, and delta PE is dependent on emitter base voltage. That makes complete sense, because the carriers that show up at the collector are determined dominantly by those that are injected by the emitter. So that's how much current's going to get through the collector. And furthermore, the collector is a reverse bias diode, right? The base collector is reverse biased. And we know that reverse saturation current has nothing to do with voltage across that junction, right? And so lo and behold, the current coming through here is independent of the voltage applied to this junction. Another reason why I want a current source. If I go to the bottom here, this is just inverted mode here, okay? And so in inverted mode, I have my collector injecting carriers like it would if it was an emitter. So it's in this case, this diode is injecting holes. So it's just like a diode. And of course, if this is a diode here, it should be dependent on the voltage across the diode, which would be collector base voltage. Look at delta PC. Delta PC is dependent on the collector base voltage. So I can get an exponential increase in the number injected into the base area. And then over here, now my emitter is acting like a collector. Perfect. It's a current source, okay? And the current coming out this way is just the inverted current transfer ratio. Okay, I've got alpha I here, inverted current transfer ratio, times the current that was injected here. So how much of this injected current from the collector will come out the emitter? How much gets across the base? That's where current transfer ratio. This is shown here, and the difference is current transfer ratio as it comes over here. And of course, it's a current source. So the current through here is independent of the voltage on this part of the circuit. And lo and behold, I look at delta PC here. That's voltage on the collector base. So this current source is dependent on voltage across the collector base, which is what I expect, because in inverted mode, the base emitter junction is reverse biased, and the current across a reverse biased diode is independent of voltage applied across it. Okay? Last thing I want to note is that in all these circuit elements, okay, you see I've got these P sub n's. So why are those in there? Well, specifically for the diodes, it's easy to figure out. Again, if I substitute delta PE in here, okay, the P sub n's cancel out and I end up with just I naught times the rest of the diode equation. So this dividing by P sub n just makes this a diode equation here. All right. So, now you can wire this thing in any way you want, okay? Here's normal mode, here's inverted mode. And clever analog circuit designers, they leverage this. This is much more flexible than a FET or something else. I could put this in a circuit, I can run it forwards, backwards, etc. And this model will let me predict what the current flows will be without having to go and derive all those hyperbolic trig functions again and all that other stuff. Okay? Another way to visualize both our normal and inverted modes is here's normal mode. Okay? Normal mode, yellow box here, forward bias a diode, hole injection into the base, right? And my collector's a current source because it's a reverse bias diode that collects holes as they go out here. And it doesn't matter how big the cliff is, once you fall off of it, you're going off to the other side, hence it's a current source, okay? And the difference between the twos is current transfer ratio, how many actually make it across the base without recombining. Here's my inverted mode, okay? Now my collector is forward biased, so green and green circled here, forward biased. I inject holes, they drive across the base as a concentration gradient, and now my emitter is a reverse bias diode, and it does the collecting. Okay, so you can see how all this pulls together. So again, they're just diodes. I can't emphasize this enough for these, my normal mode and my inverted mode. Again, the current sources have nothing to do with the voltage across those junctions. And again, the yellow and the green boxes are just simple diodes. We'll do it for the yellow box, okay? Take the emitter current in normal mode, and let's see what we get here. Let's do this whole circuit component in just normal mode, which is current in this direction. Well, I know that when I have a BJT in normal mode, this junction is reverse biased, right? Well, if I have a reverse bias junction, okay, if I plot my whole concentration across the BJT, where this would be my base width, I know that as I get to the collector end, out here, the collector end, it goes to 0 because it's a reverse bias diode. So delta PC is 0 and delta PE is an excess, right? We showed that earlier in this lecture. Well, if delta PC is 0, then this whole term goes away. If this is 0, this term goes away. I can get rid of this. I can get rid of this. So all I'm left with is this term, because delta PE is not 0. It's higher at this end. And so let's just make sure this is a diode. Well, in normal mode, I could substitute this in. I put delta PE in. I make the substitution. And, of course, it turns out to be just a diode at the end. So, here's the cool thing about the BJT's coupled diode model. You can really trust the model. So let's ask ourselves what all our currents would be, first off, if both the emitter base and the collector base were reverse biased. So what would happen if I reverse bias both of these sections of the BJT? How big would my currents be? Well, if you reverse bias these things, if you reverse bias a diode, right, my excess carriers at either side of the base goes to 0, right? It would be 0 here and 0 here at both edges of the base. Again, it would be 0 here and 0 here at both sides because both sides are reverse biased and all the carriers are falling off the cliff. So if it's 0 here, that's delta PE. That term goes to 0. This goes away. This term then goes to 0. That goes away. If it's 0 for delta PC on this side, delta PC goes to 0, that goes away, and this goes away as well. And so this would tell you that basically it would be like an open circuit here between all three terminals, which makes sense because in a circuit, reverse saturation current is much, much smaller than the current you get through a BJT. So this model just showed you this thing would basically go completely open circuit from a circuit design standpoint if these were reverse biased. I know there's a little bit of reverse saturation current, but it would be negligible for typical design. If you wanted to account for it, you could, but you don't need to worry about it typically for simple design here. Okay? And it is a little bit more, if you want to go into the finer detail and you say, well, okay, this isn't 0, you're right that if you look in here, you'd have I naught times -1, and you could still put the I naughts in here, but again, just forget about it. The model basically tells you the currents go to 0, the BJT becomes pretty much an insulator. Here's a tougher question. Let's think about this. What would my base current be, large or small, if I had symmetric doping, meaning the doping on both sides was the same for the emitter base, and I forward biased both the emitter base and the collector base? So let's assume that reverse saturation currents are all similar. My current transfer ratios are similar as well because I doped the emitter and the collector the same. And I decide to forward bias this side and forward bias this side. What's the model tell you? Well, it's very interesting. The model tells you what will the correct answer there as well. So think about this, okay? So you're not going to get the case. Your first reaction might be like, well, if I forward bias here and I forward bias here, I get a ton of current coming out the base. That is not the right answer. Look what happens. If I forward bias this side, I get a current coming in here, but I also have current coming out here. If I forward bias this side, I've got current coming in here, and I've got current coming out here. If these are the same, you'll see that this is equal to this, so they cancel out. This is equal to this, they cancel out because the same doping levels. And so it says your base current, if the current coming in and out here and the currents coming here are all, these are the same, they cancel out. These are the same in the opposite directions, they cancel out. No base current. So does that make sense? It says that if I forward bias both sides at the same time and it's symmetric, I would have no base current. Does it make sense? Well, it does, because even if I got to the point for the BJT where I forward bias this and I build an excess of holes here, I forward bias this and I build up an excess of holes here, the problem is I have no concentration gradient to drive them in either direction, right? If I have the same excess here as the same excess here, because I forward bias both of these, there's no concentration gradient here to drive them either to the left or to the right. So then the last thing you have to ask yourself, well, okay, so I've got no net current in either direction because I've got no concentration gradient for the base, but what about all these holes sitting inside the base? Aren't I going to get a lot of base current as electrons recombine? Well, no, you won't, because the whole point of how we designed the BJT was that the base is lightly doped and very narrow. It's so narrow that from a simple circuit standpoint, you forward bias this, you forward bias this, you pretty much still have very small or no current here. And so this tells you exactly what you expect. You forward bias both of these, and again, you get pretty much no currents through these things for the case where it's symmetric. Now, if it was asymmetric, right, and I forward bias this side and this side, I could end up with more here, more holes on this side and less on this side, because this could be heavily doped p-type. So I get more holes coming here. Then I would start to see actually some net current flow. So the model would show you the right answer for that. And so again, the key point is trust the model. It's beautiful because now you can put bias on this, how you should do a BJT, how you even shouldn't do a BJT, and it still tells you how it would work in a circuit. And really good designers will use this model to put in a circuit and bias a BJT in ways and understand what is happening without having to look at all this semiconductor stuff, just looking at simple diodes and current sources to predict the behavior. Now, again, they're all are alternate representations. I'm not going to go in these. These are in your book in section 711. If you want to look at them, you can, but they just move some terms around and they come up with some other models as well. All right, let's do some review now, and then you're done with the coupled diode model. So first question, does the model have to be symmetrically doped for the emitter and collector? Does this model have to be the same doping levels on the emitter and the collector? Here's a hint. There are two things in the model over here, two terms that depend on doping. You should know what they are. They depend on the doping on the emitter side versus the collector side. We talked about it back in the lecture slides. Second question, why the current sources? Your hint there is that, again, think of the basic definition of a current source and note how the current source is dependent on delta PC or delta PE, and for example, delta PC is not voltage across this terminal. It's a voltage across another terminal or another node of the circuit. And so that should kind of fit the basic definition of a current source. Question, if both the emitter and the collector base are positive or forward biased, okay? If if I forward bias both of them, what will my base current be and why? Is it very large, very small or zero, so negligible, or the model doesn't tell me what I need to know for that? Okay? And why? You should go back to one of the previous slides and understand why it is as well. There are two key points. One was mainly related to current components canceling out, and because the base width is narrow, that even if you have a lot of holes in here, you just don't have a lot of recombination because the base width is so narrow. There's not a lot of area for recombination. Next question, how would you change the model if WB became really large? So let's basically take our BJT and expand a really wide base. How would the model change? Well, here's your hint. If I have a really wide base width, would I have a BJT? You should be able to answer that. And if I don't have a BJT, then you should be able to eliminate 2 of my 4 circuit components here. 1, 2, 3, 4. 2 of these should go away. Which ones will go away? You should be able to answer that. And then you'll see what you would expect to see if you basically had, really wide base, PN junction, with a really wide base in between 2 PN junctions. Would the specific BJT shown it right, this specific BJT here, run better in terms of higher amplification in normal mode, inverted mode, or would it be the same for both modes? Here's your hint, look at the emitter and collector dopings. Last one, and this is easy, if you fed in all the terms for the boxes in yellow and green, so feed in all the terms in here, what do the equations reduce to? A diode, a current source, or it can't be solved? That's an easy question as well. Alright, looking forward to seeing you in class.